All right, let's get started. So I extended the project deadline by a week. So it's due next Friday instead. And I did that because there was a just absolutely catastrophic type in the project spec. So the original example was, me telling you that if you have sensing, okay, I brought this. Let's see if this goes. There we go. Where if you have England and England links to UK and you have Great Britain and Great Britain redirects to UK and England links to Great Britain. Is that right? Yeah. Yeah. Okay. If you have this kind of situation going on, you have Great Britain redirecting to UK, if you have UK linking to England and England linking to Great Britain, then you're supposed to replace Great Britain with UK. So the resultant pair is going to be England, UK. In the original example, the resultant pair was England, Great Britain, which makes absolutely no sense in Britain as a redirect. So I'm sorry about that if that was confusing, because that was confusing. Are there any other questions on the change to the spec? Okay, good, because on Tuesday after class, I had several people point that out to me. I'm like, oh crap, what have I done? Okay. All right. So to make up for that, I've extended it by a week. You're welcome. So, project questions. We got all the time in the world today. We're talking about DynamoDB. Yeah.
Like actually, are you learning more about this as well? And put it in the bucket or you doing something?
No, I will use exactly 0 things from your buckets.
Okay, so when I'm even starting one is sending a zip file and the baby codes. You can send it to our back, so it doesn't have to send it to the comments. It's code. That's just an example.
Well, so I will personally change like my interactive EMR script to upload your zip file to my location.
Okay. You don't want to use our slot.
Yeah, I'm not going to use your start EMR. I mean, any other questions?
So you want this a zip file and you get a read on?
I want instructions on how to make a zip file if it's necessary. So if you choose to put your entire program into the entry point file, I actually don't care because my program is all in one file anyway. It's like 70 lines of code total. You do not need to split something like that up into multiple files. So if your program is short enough to be one file, just put it in one file. Anything else?
Can you just put like zip file if you have to share providing that one individually?
Yeah. Other questions? Okay, cool. Let's talk about Dynamo. All right. So we remember last time that we were talking about databases and data warehouses. And we talked about data warehouses in the sense that they are meant to, they're designed for high throughput and maybe higher latency applications. So if you need to do something in batch, and you need to deal with a lot of data at the same time, you would use something like Snowflake. You'd use a data warehouse. A database is the opposite use case. It's where you don't necessarily need to deal with a lot of data at the same time, but you need the response to be quick. And this is where DynamoDB comes in. Now, Trina, I know you asked a question on what constitutes a NoSQL database last time, and I didn't really fully answer the question. And hello? And we'll talk about that right now. So, when it says DynamoDB is a NoSQL database, what does that mean? And I basically answered that as it doesn't use SQL. And that sounds obvious from the name, but it doesn't necessarily mean anything because, like I said, SQL is a syntax. It's a syntax to describe a query to a database. So you can have a NoSQL database that will use SQL syntax. A really good example is another distributed database or another NoSQL database called Cassandra, Apache Cassandra. So Cassandra is kind of like DynamoDB. I think it's called like Cassandra QL. Definitions. Is this just going to be, this is a context-free grammar. I don't want to see that. This ain't a compiler's class. I just need examples. Okay, there we go. All right. So this looks like SQL, right? This is Cassandra query. You can't see that. This happens every time. This is Cassandra query language, and that looks like SQL. So because Cassandra is a NoSQL database, you can still kind of use a subset of SQL, and this looks like SQL, but there are certain features in a SQL database that are not available here. And among those is the enforcement of the foreign key constraint, like we talked about earlier. Now, can someone tell me what the foreign key constraint is? Yeah, but in terms of the actual constraint, what does it enforce? So that kind of depends. You can actually kind of set the relationship, right? So if you look at like Postgres foreign key options, I think foreign key option, foreign data, nope. I don't mean data from another source, constraints. Okay. So it's, where is it? Cascade, on, delete, restrict. What does restrict mean? Every database has a different syntax for this. Ah. Okay. So it depends on how you configure it. Why do I keep doing this? So it depends on how you configure it. So let's say right here you have a person database and you have an ID column, which is just a number. You have a name, blah, blah, blah. And then you have a department. Then you have a department ID and department name. And now you want another table to keep track of which people are part of which department. And this could be like let's say it's a many-to-many relationship. So you can have one person be part of multiple departments, and you can have departments have multiple people. So this department person table, keep doing this. I need to not do this on the whiteboard because we have people on Zoom. So we have person, and they have an ID and a name. Whoa, that wasn't supposed to be executed. And then we have a department, and then they also have an ID and a name. And then we have a person department table, and that has a person ID and a department ID. And that tells us which people are part of which department. Okay, so in this case, ID would be the primary key for person, and ID is the primary key for department ID. And so this column references a row somewhere in the person table. This column references a row somewhere in the department table, right? And since this is a primary key, the SQL database who has this table is enforcing the constraint that this ID must be unique. There is only one row in this table that has this ID, and exactly one row. And the same thing with department ID. So if a particular ID exists in the department table, only one row has it. Right? Right. So the foreign key constraint will basically say if a row exists in the person department table, that means a row containing these two IDs must also exist in the person table and the department table, respectively. Now, which one you use, which of these constraints you use when you delete a row will affect the behavior. So if you choose the cascade option, where did it go? Yeah. If you choose the cascade option, what happens is when you delete a row in the department table, it will find every other row in every other table that references that row with a foreign key and also delete it. That's the cascading part of the foreign key constraint. So if we have, the CS department and BSU decides to delete the CS department for whatever reason, that means that every person department pair and that which is part of the CS department. So every person department pair linked to the CS department will also disappear from that table. This is the foreign key constraint. This is not present in a NoSQL database. So that's what they mean by NoSQL, is that they don't have these kinds of constraints available to them. So that's one thing. Another thing is that most NoSQL databases will not allow you to do joins. So one of the secrets to why joins are so efficient in a NoSQL data or in a SQL database is because many tables in a SQL database are indexed. So you know that if you have a table in a NoSQL database, if you have two tables in a NoSQL database, and they're both indexed on the key that you're joining on, you know that the join will be much faster, right? And the reason for that is an index is literally just a sorted list of rows, and they're sorted by that key that they're indexed on. So, and there are different types of indexes. The most common is a B-tree index. And so when I said B-trees are used for indexes in, Postgres, this is what I was talking about. B-trees are used to implement indexes. And so when you need to insert a row into a table that is indexed on one or more columns, it will insert a row into this B-tree that is representing the index. And this is an efficient insert because B-tree has basically logarithmic time for all of its operations, which is nice. But it works in a slightly different way because most NoSQL databases are distributed systems. And so the thing about a SQL database is that they run on one server. It's a single machine. So this is the tech stack that we built in the older version of Count's product, Count Command. Count Command is a bunch of boxes running in Palo Alto somewhere in a data center. And one of those boxes is the Oracle SQL database. I think we have 5 boxes for Oracle. We have the Oracle SQL database. And the Oracle SQL database is a monolithic SQL database that doesn't really expand very well beyond a few servers at most. NoSQL databases are designed very differently. And they're designed in such a way where they restrict the kinds of queries you're allowed to execute on them, but they scale much more effectively. So Dynamo, in the case of Dynamo, your keys or your rows can be split among probably as many servers as you could possibly imagine. They can be split among so many servers, but the efficiency doesn't change because, and I'm just guessing at this point, this is part of what my master's project was, is DynamoDB probably implements some kind of consistent hashing distributed hash table or something. And the consistent hashing would be you have, a list of machines that are storing your data, and all of the other machines will keep track of how many other machines there are in the cluster. And, usually there's not like billions of machines, maybe there's a couple 10,000 or something like that. So every machine in the cluster may have a list of every other machine in the cluster. And so when a request comes in to this system, you can hash the key that you're requesting for this request, and it will take you to that specific node in the cluster that handles the data or that has that piece of the data. So we're going to see this when we actually create a Dynamo table. All right, let's create a table. What do we want to name it? What are we storing in this table? Give me some ideas. I'm not feeling creative today. Huh? All right, perfect. Dinosaurs. All right. So what's going to be our partition key for a dinosaur? The scientific name. Okay. Actually, no. What is, man, I forget what this was. Like, how we have that taxonomy for classifying animals, and it goes all the way down from kingdom into phylum into genus and whatever. What's the next one up from species? Does anyone know that? Huh? It is genus? Yeah, okay, we'll just call it genus. Okay. And the sort key is going to be species. And they're both strings. And the partition key can be either it says binary, but that it's really just it's another kind of string. So it's a sequence of bytes of variable. That's what binary is. And it can also be a number or a string. In this case, it's a string, and the sort key has the same options. And in this case, it's also going to be a string. Okay. So we're not going to set the table capacity or the scaling or anything like that because I don't care anymore. We're just talking about the data model. Okay. So this is how it works. So are you still, is it still creating? Is that why? There we go. Okay. Are you going to close anytime soon? There we go. Can we can insert that. All right. So you need a dinosaur. Velociraptor, is that the species? Okay, it is genus. And then, okay. That's a species. All right. So the partition key is the Velociraptor genus. The sort key is this thing that I can't pronounce, species scientific name. And we want to add a new attribute. And what do we want to know about this species besides what it's called? We can look at the common name. What's the common name for whatever this thing is? Okay, that's great, but does it have a common name? Huh? Okay, I'm just gonna call it a tooth chicken for a common name. Okay. What else do we want to know about it? Average weight. And let's say the average weight of a tooth chicken is what? 300 kilograms. Okay, I'm in trouble if this thing finds me and figures out that I call it a tooth chicken. All right. So now we'll create the item. All right. So Dynamo has, at least on the outset of it, two different operations available to it: scan and query. Scan will iterate through the entire database. So it'll iterate through the entire database row by row, and this is super slow, especially if you have a large Dynamo table. Like the biggest Dynamo table I've created, at least at count, has 24 billion rows in it. This is a giant table. You cannot scan through this table. The other option is to do a query. Now, when you do a query, you have to select a partition key to query on. And the partition key, being the genus, is Velociraptor. And right now, we're not going to specify a sort key value. So we want every Velociraptor in the Velociraptor genus. Okay. And so we find this out. So what if we wanted to create another Velociraptor? Let's create another one. Does anyone know another type of Velociraptor? Help me out here, guys. There we go. Yeah, there we go. Okay. All right. What's this thing's common name? Yes. We can add different attributes to different records. Yep. So we can actually add something completely different. We can add like sure, diet. And actually we're gonna oversimplify this a little bit, and we're gonna say its diet is, I'm not even gonna call it diet. I'm gonna say is carnivore. And that's gonna be true. Then we can create the item. All right. So now when we query this genus partition key with the genus Velociraptor, then we see two different ones. We see two different items show up. We see one, which is the tooth chicken, and the other one, which has an unknown common name because I've never heard of it. And it's a carnivore, whatever that is. So Dynamo is pretty cool in the sense that you can have the partition key and you can have the sort key, but every other item or every other attribute in the item is flexible. So you can put whatever you want in here aside from the partition key having to be the type that it says it is, and the sort key having to be the type of the table expects. We can make a table with a different type of sort key and a different type of partition key if we wanted to. That particular 24 billion row table I talked about had a partition key with a string type and a sort key with a number type. This is the flexible CI queries that I was talking about. All right. So we haven't actually seen anything outside the Velociraptor genus. So what else are we going to look for? Um, Penguin. Huh? You can only query on partition keys. If you want to query on a sort key, you can, but you need a partition key. So the partition key identifies, it's how the hasher among those different machines in Dynamo actually finds the node in the Dynamo cluster that that row lives on. So if you don't have the partition key, you don't know where the row lives and you can't find it.
Okay, so what if we want to serve two different
You can do two different queries.
separate queries?
Yeah. So it's one query on the first genus and the other query on the second genus. So apparently, according to science, penguins are at least somewhat related to velociraptors. Maybe. Where did it go? Okay. Penguins. This is going to be a yes. All right. And we're going to create another thing, which is feather density. I don't know. And it's going to be 4 fluffs per floof. Okay. Okay. So if we do a scan, you can run the scan. And now we have all 3 of these. And you'll notice that in this view, it's updating it based on every single different column or different attribute that appeared in the scan, which is honestly kind of annoying, but whatever. So when we query it, and we query the Velociraptor genus, only things within the genus Velociraptor show up. So we don't see penguin over here. We can also see penguin separately, and all the Velociraptors will also disappear. So the other thing that we can do that's pretty cool is we can specify a sort key. So, as the name suggests, within a partition, so everything that with the same partition key and everything within the same partition key is also co-located. So it means that like everything in the Velociraptor partition is stored in the same place. And so in that place that all the Velociraptors are stored, those rows are sorted by the sort key. So you can basically do a binary search within that partition to find a specific row that you want to find. But what's also cool is that you can take, really, I'm on call right now, and for some reason QA is bugging. Okay, what was I saying? Oh, right. You can take the sort key and you can select a specific sort key and then take everything after that or take everything within a range of different sort keys. So that's very powerful. And it's also something that we haven't used yet, but we're planning on using it in our identity product is using the sort keys for this technique. Is what we're planning on doing is we have a bunch of timestamps that are associated with fraud transactions, and we want to find out what is the closest piece of fraud that occurred in the last 90 days. And so even though we don't have the specific sort key value for that timestamp, we can basically just say, all right, within this particular individual, so the individual is the partition key, look through all the fraud that they've ever committed. What is going on? Look at all the fraud that they've ever committed with this sort key, with this timestamp. And even if we don't have a value in the database for that timestamp, it will still iterate through them in order. So it'll basically say, let's say we had a fraud transaction occur at timestamp 3. And then we had another fraud transaction occur at 5, and then at 8, and then at 9, and then at 12. So what we're asking is, okay, what is the most recent piece of fraud that occurred after, after timestamp 6? So we would query it based off of timestamp 6, and we would say, all right, when you're querying on this, I want you to go descending. So we're going to start at the bottom, which is 6, and then go up. So 6 doesn't exist, but that's what we're querying based off of. And then this is going to return every piece of fraud that has occurred after the number 6, even if 6 isn't actually in the database. Well, yeah. So this is within a particular individual. So the individual would be the partition key. And we have a bunch of fraud sorted within the partition by timestamp. So the timestamp is the sorted key.
Okay, so within your partition,
Yes. Within your partition, you can query on the sort key and iterate through them in order, which is cool. And I can show you an example of that. So let's add another item, which, let's see. We have a penguin, and it is another type of penguin that starts with E, Easter Island penguin. I don't know if that's a real penguin. Okay. And then what else are we gonna have? We're gonna create another penguin. We're gonna say it's an Antarctic penguin. Okay. So when we do a query on when we do a query on penguin, all 3 of these are going to show up. Okay. So then, what if we wanted to do only every penguin species that starts with E and greater? So we could enter a sort key value of E, and then if we start descending, we should just have everything that starts with E. Yo, I'm not okay with that. Oh, equal to. Greater than? Yeah. Okay, there we go. Okay. So, and you'll notice that all of these are within sorted order. What's kind of cool is that you can also select a between, and you can also select begins with, because begins with is kind of the same thing, at least for strings. So we can say it has to be between E and ED. So if it's between E and ED, then it's going to contain Easter Island penguin, but it's going to exclude Emperor penguin. There we go. Questions so far? We use Dynamo religiously at Count. We use this all the time. So this is it's about latency. It's about what this data is supposed to be for. So we want this data as quickly as possible. We want this data with low latency. Let's say we have a user on the front end that wants to know something about everything in the penguin genus, right? They want to know everything in the penguin genus, and we want to get this information within a few milliseconds. We would use a Dynamo database. With Snowflake or with another data warehouse like Snowflake, we might have we might have like a minute of latency. I mean, you've seen Snowflake. Sometimes it takes a fat second to start up a query, right? So this is specifically for low latency applications. That's part of the guarantee we get from using Dynamo, is we know that a call out to Dynamo is not going to take very long in comparison to a call out to Snowflake. So even though Dynamo can't process very much information at the same time, it can process a little bit of information really quickly, and that's what we want.
And then we're using the those together instead of CPM is
Yes, it's because of the quantity. Like in this example, we only have like 5 elements in here. But we have several tables at count with billions of rows in them, and that 124 billion row table I created has 8 terabytes of data, and that's with the data like compressed about as far down as you can go. So yes, you have to have a specific use case in mind. That is a key difference between SQL databases and NoSQL databases, is that in a SQL database, your queries are flexible, right? You can do a lot with the combination of select, filter, and join and group by. You can do a lot with those. With Dynamo, you have to know how you're going to access your database ahead of time, and you have to design your database according to how you plan on retrieving the data. Because in Dynamo, it's basically only a select statement. That's all you have. You don't have a filter, you don't have group by, and you sure don't have join. You don't have any of those tools available to you. So you have an index. You can make indexes in Dynamo, and we'll go through that in a second. So you have indexes in Dynamo, and you have your partition keys and your sort keys in Dynamo. And that's all. Questions so far? This is how we do big data analytics in real time. It's a combination of Spark and DynamoDB. What's Spark's part is Spark will basically pre-aggregate a bunch of data ahead of time and then load it into Dynamo so that we can retrieve it quickly. So Spark is one side of the coin when we actually calculate the data. Dynamo is the other side of things where we need to retrieve the data in real time when a customer makes a request. And that's the funny part, because it's usually different people on our team who deal with these tools. Because for Spark, it's usually the data scientists who are using Spark. But the machine learning engineers almost exclusively use Dynamo. I've never seen a data scientist use Dynamo because they don't need to. None of their work deals with real-time applications.
So you're not using Spark to update it. You're using Dynamo or the Dynamo.
That, yes.
That's what.
So the way the way we've done this has evolved over time. So what we used to do is we used to have Spark running to repeatedly insert things into Dynamo from Spark, because Spark has a lot of parallelism available to it. And so it can write different things to Dynamo in parallel, all from a bunch of different nodes from a bunch of different cores at the same time. So that's nice. What we do now is we actually figured out that whenever we do like a new aggregation, we're creating entirely different numbers every time. So what we do instead is we will take the data in Spark and kind of munge it into a DynamoDB format. And DynamoDB actually allows you to take a prefix of files in S3 and import it directly into a Dynamo table. So that's what we do now. The difference, though, is that when you import a Dynamo table from S3 into Dynamo, it has to be a brand new table. You can't import from S3 into an existing table. Don't ask me why, I don't know. Having that functionality for an existing table would be real nice, but we don't have that right now.
But that's a limitation of Dynamo.
That's a limitation of Dynamo.
And is this Dynamo database not giving a Dynamo story?
No. Dynamo is its own storage. So it will
Don't store it.
it's its own service, its own storage, it's all separate. So when you import a Dynamo table from S3, Dynamo now owns its own copy of the data. So if you remove the stuff from S3, the Dynamo table will still have it. So Dynamo table now owns its own copy because it's organized in a fundamentally different way in Dynamo than it is in S3, right? Because in Dynamo, everything's organized according to the partition key. In S3, that's not true. In S3, it's just a jumbled mess. It's just a bunch of files. Anything can be anywhere.
Okay. So is it immutable?
Is Dynamo immutable? No.
Okay. So you can look up stuff and change anything.
We can change it. Huh? You can add a bunch of records in batch to it, but it's significantly slower than adding a bunch of records to, say, a data warehouse table. So it's significantly more expensive to add stuff to Dynamo in batch, and it takes long. And money-wise. Amazon charges based on how much data you're storing in Dynamo per month, and they also charge based on the number of write requests you submit to it and the number of read requests. So they charge for storage, they charge for reads, and they charge for writes, and all of those costs are different. So they have one rate for storage, another rate for read costs, and another rate for write costs. So we can change an item. So let's just scan the table. All right. So let's say I'm a naturalist and I'm doing science, and I figure out that actually emperor penguins have 8 fluffs per floof instead of 4. So now we can save that. And that change is now reflected in the row that we read from that. Maybe it's gotten colder in Antarctica. I don't know. So you'll notice that in a scan, here's the difference between a scan and a query. A scan does not require you to submit a partition key. So you'll notice in this, kind of form, there's no entry for a partition key. In a query, you have to enter a partition key, right? And the reason for that is a scan goes through the entire table. A scan will iterate through all of the rows in the table. And for this table, it's efficient and it's fast because we only have like 5 items in the table. But if we had a table with many more rows than that, then a scan is super slow. You will never do a scan in real life. Like in a production workload database, we'll probably never do a scan. Because if you can do a scan, it means that you have enough data to not use a NoSQL database. So you'll pretty much...
Like, if you don't have enough data to push you in the you will choose this focus on protection, but
So that's the case that I would use, but there are other reasons too. So, this is where we get to the opinion part of the lecture, is that I think that people are a little bit too gung-ho with the NoSQL thing, in the sense that they will use NoSQL even if they don't really need it. So they don't necessarily have enough data to warrant using a NoSQL database or something like that. But there's additional things that make a NoSQL database nice too, in that it's not just the amount of data that it scales well with, it's the traffic that it scales well with too. Because a NoSQL database can pretty much handle any volume of writes that you want to submit to it per second. You want to submit 40,000 writes to a NoSQL database per second? That's fine. It'll just make more servers, and you can do that. If you want to...
all do the same partition.
No.
Okay.
That you just mentioned something called hot partitioning. That is a very astute observation, because If you do a bunch of writes to the same partition, it will not be efficient. So when I said 40,000 writes per second, I was assuming that all those writes are to independent partition keys and everything. If you do a bunch of writes to the same partition key, it does not scale. It scales in the same way a SQL database would, as in poorly. But for a SQL database, since it has to keep all the data integrity intact, then you can only do writes on probably a couple of different nodes at once, because it has to manage this coordination between nodes to make sure that you don't have any contradictions between these writes that you're doing. Does that make sense? So your scalability in Dynamo is way better than your scalability in SQL. And that's the thing. Like for a lot of our applications, once we offload the data into Dynamo, we don't edit it at all. And so the coordination that you would have to do to perform writes doesn't matter because we're not doing writes. So we could store a lot of our data in a SQL database instead of Dynamo if we wanted to, because it's not that much data. It's less than a terabyte. And we're not doing any writes. So we can make as many copies of the data that we want to. Everybody with me? Good, good.
Yep, and it doesn't matter how many reads for simple versus no simple.
So you can also have hot partitioning for the reads in a NoSQL database. So because a particular partition is still like maybe only a couple of nodes in a Dynamo table. And so you'd still be overwhelming that same node with all the traffic. So you can have hot partitioning for both reads and writes in a NoSQL database.
Okay, so in my web development, do you feel like most people are looking to develop to where something like a NoSQL backend rather than the SQL database so that they can not worry about scaling?
Yeah, so people when they build web applications are taught to anticipate that your data and your volume will grow. And when they do that, their automatic response is to make everything a NoSQL database because that just scales better than SQL databases do. The problem is that a lot of the time you might not necessarily ever reach that scale. And if you never reach that scale, then your database is not going to have the same flexibility as a SQL database does. One of the other benefits to using Dynamo, though, specifically, is that it's serverless in the sense that you pay for storage and you pay for the requests that you send to it. You don't necessarily pay for uptime. That's not the case with a SQL database, at least in AWS. Because in AWS, you have to allocate an instance to run Postgres. And then that instance is just sitting there, even if there's no request coming in. You still pay for them. So that's the other great thing about Dynamo is that it's serverless in the sense that if you're not using your Dynamo table, you don't pay for anything except the storage. But in a SQL database, you pay for the storage uptime. The uptime is way more expensive than the storage is.
I still have very fault tolerance too, since it's spread out.
So that's the other thing. Fault tolerance is mostly about how many replicas you have and where those replicas are stored. So depending on how your SQL database is replicated and depending on whether or not you're performing writes, SQL may or may not have more reliability. So let's say we were never doing any writes in our SQL database and we can make as many copies as we want. It's just as fault tolerant. Any other questions? You want to make an index? Let's make an index. Yeah. Okay. Let's see. Dinosaurs, indexes. Hello? There we go. All right. Let's create a global secondary index. What do we want our index to be on? Let's say our index is on the common name. And then the sort key. Let's do the species. Actually, let's do the species for the sort key. Common name species index. And then okay, attribute projections. We're gonna project all of the attributes into the table. So basically, if an attribute exists in the original item or in the original row, then we're also going to see that attribute in the indexed row. It's still creating the index. So an index is in DynamoDB is basically the same concept as an index in a SQL database in the sense that it allows us to efficiently query the database on different columns. So you can create a new partition key for an index. Yes. Yes. So an index, a global secondary index will duplicate the data because it has to key it differently. So your original row is, Velociraptor tooth chicken, and then, the global secondary index is going to store that same row in a potentially completely other place, and this time it's keyed on tooth chicken instead. It's still creating. And the cool thing about indexes is that they react to changes that you make in the original table. So if you delete a row in an index, or not an index, if you delete a row in a table, then in the index, that same row is deleted. The difference is that in Dynamo, the delete propagation is what's called eventually consistent. So what that basically means is that when you do a delete in Dynamo and then you do a read from the index, it's not guaranteed that the read from the index is going to reflect that deletion immediately. It might take a few minutes. So the consistency guarantees are different from what you would get in SQL. Because in SQL, if you have an index, if you delete a row in a SQL table, and then right after that you query the index, you know the row is going to be gone. Because SQL databases have that consistency guarantee, right? That's part of ACID compliance. No SQL databases are not ACID compliant in that sense. Is this thing created yet? Really? All right. Any questions about DynamoDB? I'm just waiting for the index whenever that happens. You can also back up the Dynamo table. You can also make the table global. Like I don't think we've talked about this before, but Dynamo tables by default are local to a particular region that you created in. So if you look in your upper right-hand corner, you'll see a list of regions in here, and a region is just a group of data centers that AWS has. Because when you're dealing with large-scale distributed systems in real life, location really, really matters. And so instead of abstracting that out, they just expose where you're deploying your stuff directly. So you can choose where you deploy your stuff. And this really matters because the speed of light isn't actually that fast. And the speed of light is the limit for how fast we can transfer information. Usually it's a lot slower than the speed of light. Light takes about 120 milliseconds for a round trip around the globe. That's slow. Our expected response time in count is 250 milliseconds. So it's twice that. So we have to do all of our fraud analytics and all of our, all of our rules evaluation and all of our counters and all of our machine learning influence, all in the time it takes for light to circle the globe twice. That's how much time we have, which is not a lot. And so where your deployment lives affects your latency, especially, you've had this experience. If you're trying to talk to a service that lives on the other side of the world, it's significantly slower because maybe they're not deployed globally. Mm-hmm. So that's what these are. Is the index there? There we go. I wonder if we can query select table. Do we not have? Oh, that's cat. We have an index. What are you talking about? There we go. Now we have an index. So now we can enter the common name. And I spelled that wrong. Emperor penguin. And since we have an emperor penguin in here, and no, that's the common name. The only thing with the common name is the tooth chicken, so we have to say that. All right, there we go. So now we can query Velociraptor on tooth chicken. It's official now. And you can see that even in the index, it has all of its attributes. So it has the original partition key and it has the original sort key along with it. And it has every other attribute. And you can scan through an index also, but you would never want to do this normally. And you'll also notice that the index only has one item in it because there's only one item in this table that has the common name attribute defined. So if we define another item with the common name attribute, then it should automatically propagate to the index. So if we go back to the dinosaurs table and we add a new attribute and we add the common name attribute. And Emperor Penguin is going to be sushi. So then if we query the index, we should have it queryable under the common name sushi. There we go. So the change we made to the original table automatically propagated to the index. Yay. This is how we do big data in real time. Is we pre-calculate everything and we stick it in the Dynamo table. I don't think I have much else to say, so we might be done.
Okay, so this is used for the quick block. And then I use the data around for the flexibility that I'm changing the data that's stored in that. So I James and Jen and those real accessing between
Databases.
they're not that
Dynamo can be used for that. And it is used for that.
Right.
So the persona system in Count, at least in the new version of Count services, is implemented in Dynamo. And the persona system is it's a database that implements what's called dynamic connectivity. So, when we were talking about graphs and we did the connected components with the graphs. So dynamic connectivity is how do you calculate the connected components in real time? That's what Persona is. Persona does that with Dynamo. And that graph is constantly changing because we age out transactions after a 14-day window in Persona. So it's basically saying these transactions, they form a graph, find the current connected components as they are, and we'll delete nodes in this graph after 14 days. So the connected components are always changing. So what Persona does is when it receives a transaction, it calculates the connected component in real time, and then it will add the transaction it just got to the graph. So it's doing both the real-time querying and the consistently updating as well. So Dynamo can also be used for, real-time reads and writes, user interaction sort of thing. So Dynamo is a full-fledged database in every sense of the word. You would use it for the same purposes that you would use a SQL database for, except the use cases are different in the sense that it scales differently and its consistency guarantees are also different. They do. It's called Aurora or RDS or whatever you want to call it. And when they say relational database, they're talking about a traditional SQL stuff. More questions? All right, we're done.